So this is chapter 5 on stereoisomers. An isomer means same parts. So isomers so far have been divided into constitutional isomers that have the same molecular formula but a different connectivity. The atoms are put together differently. And we're given the example here of an ether versus an alcohol. They have the same atoms, but the atoms are put together differently. Isomers are also stereoisomers. These also have the same molecular formula, like constitutional isomers, but they're put together, the atoms are put together in the same order, but with a different spatial arrangement. So here we have an example of a stereoisomer. It's a cyclohexane. They have the same atoms, the same formula, and even the same connectivity. We've got a carbon with a methyl group and a carbon with a methyl group, but the methyl groups are arranged differently. Here, they're both on top of the molecule. Here, one is above and one is below. That makes them stereoisomers. As we talked about isomers, we'll be talking about chirality, and chiral objects and achiral objects. So, achiral objects can be superimposed on their mirror image. Their mirror image is identical. And these objects, these achiral objects, are symmetrical, and they have a plane of symmetry. So if we look at our chair here, there's a plane of symmetry right down the middle. The left half is the same as the right half. Chiral objects, however, cannot be superimposed on their mirror image, and they lack a plane of symmetry. So if we have these two chairs, they're not symmetrical, and they can't be put on top of each other. An example of something that's achiral would be socks. It does not matter whether you put your left sock on your right foot or your right sock on your left foot. They're the same. But your shoes are chiral. You can't put your left shoe on your right foot and be comfortable. Hands are chiral. I can't, if I put them on top of each other, I have thumbs on the wrong side. So that makes my hands chiral. Screws are going to be chiral. If we have a mirror image of a screw, a left-handed screw would not be the same as a right-handed screw. So that makes them chiral. But a nail is achiral. Now, in molecules, the most common chiral thing you will see is a carbon with 4 different groups. So here we have a carbon, it's got 4 different groups. On the other side, we have its mirror image. And those are chiral molecules because they're different. So let's locate the chiral centers in these molecules below. So what we're looking for here is carbons that are attached to 4 different things. So there are 2 hydrogens here, so that one's not going to be chiral. But this one has a hydroxy, a hydrogen, it has this group coming off here and the ring on the other side. So that one is chiral. This one is also chiral. But none of the others are because they don't have 4 different bonds. So let's look at the next one. We're looking for things that have 4 different things. This one has a hydroxy, it has hydrogen, it's got this bunch that the group of carbons that comes off this way, and this group of carbons that goes off this way that's different. So that would make that one chiral. This one has 2 hydrogens, so it's not chiral. This one has a double bond, and so it only has 2 hydrogens. It only has 3 bonds. So any carbon that's involved in a double bond will not be chiral because it won't have enough double bonds. This one is chiral, this one is chiral, this one, and this one. And that's all. You can go back and check. So I'll ask you the same question that I ask in class. Are these the same compound? Well, they both have black carbons in the middle and 4 different balls on the outside. But they are, in fact, mirror images of each other. That makes them enantiomers. And we can tell that they're different because if we have a site that we would like them to land on, if this was a biologically active compound, we put the yellow on the yellow, the red on the red, the blue on the blue. That one fits. Let's put the mirror image. If I put the yellow on the yellow and the red on the red, the blue is in the wrong position. If I put the blue in the right position, then the red and the yellow aren't right. So if these were biologically active, this one would not fit on the same active site as this one. So enantiomers are chiral compound and its mirror image. It has to be a chiral compound. And its mirror image. Okay, so if we wanted to draw the enantiomer of amphetamine, we could pretend that there's a mirror right here, and we would draw a ring, nitrogen right there, carbon in the up position, and that would be our enantiomer of amphetamine. But we can also draw it as if the mirror is behind the molecule. And sometimes that's a little easier because when we draw it with the molecule behind, the mirror behind the molecule, we draw the same structure except where it's coming forward, we make it go back. So if I wanted to draw this same structure, or draw the enantiomer, I could also do this. This structure is the same as this structure. If you pick this up in your mind and rotate it, and turn it upside down, this one that's coming toward you will now be going away from you. So if we wanted to draw the enantiomer of this, we could just repeat the structure. A little bit messy here. And where we have the chiral carbon, we just make it go down. These are enantiomers of each other. So we could do the same thing with propanol. We'll draw our rings first. ether. There's our amine. And there's the hydroxy. This is our chiral carbon. And instead of making it go toward me, I'll make it go away. And we have the enantiomer. Okay, so you can draw enantiomers two ways. One is by using the mirror beside it. If you do that, you flip the molecule, but you keep the stereochemistry the same. So if it's coming toward you, it's coming toward you. If you put the mirror behind, then you can draw the same structure as I did here, and the one that's coming towards you is now going away from you.